Good afternoon and welcome back. Today we focus on generative adversarial networks (GANs), one of the most exciting advances in artificial intelligence. GANs are designed to create new data images, music, or text that looks and feels strikingly real. In this session, we lay out the core idea, a generator and a discriminator engaged in a subtle duel iterating toward higher realism. We'll also discuss why GANs have become so influential across technology and the creative industries, shaping both practical applications and scholarly debates. By the end, you'll have a clear framework for analyzing GANs and for guiding future research. Today, we'll cover generative adversarial networks, or GANs, and the idea of two parts competing to create new data. We'll explain the architecture, how a generator makes something while a discriminator judges it to see how they work together to produce results that look real. Then, we'll walk through the training process, what it takes to teach GANs, and the common bumps you might encounter along the way. We'll explore variants, different twists, and improvements you'll see in practice. Next, we'll look at real-world applications, how GANs are used to make and edit images. We'll discuss challenges and limitations such as training stability and practical hurdles. We'll review tools and frameworks, libraries, and environments for building and experimenting. Finally, we'll peek at future directions in GAN research, where the field is headed and what new ideas are being explored. Now, let's pull back the curtain on generative adversarial networks, or GANs, a clever two-player setup where a generator crafts data and a discriminator tests it for authenticity. We'll watch how these rivals push each other to improve in a loop that keeps refining images, sounds, and text until they approach real-world quality. We'll note who sparked the idea, Ian Goodfellow, back in 2014 and why that shift changed how machines learn through competition. Then we'll explore practical uses across art, science, and industry, turning rough sketches into polished visuals, boosting datasets, and enabling quick prototypes in design. But with power comes challenges. Training can be unstable, outputs may cycle or hallucinate, and safeguards matter. Finally, we'll consider how to measure success and even try simple hands-on experiments to see the tug-of-war for ourselves. Building on the basics, let's turn to how researchers make GANs more reliable, interpretable, and evaluable in practice. I'll touch on stabilization techniques, evaluation metrics, and a few hybrid directions that push beyond vanilla adversarial training. First, stabilization ideas. Spectral normalization is a simple yet effective tool. By constraining the spectral norm of each weight matrix in the discriminator, we keep the network slipshifts constant under control. This dampens explosive gradients and yields more predictable training dynamics, which in turn reduces mode hopping and helps the generator explore the data distribution more consistently. You'll see spectral normalization widely adopted in state-of-the-art discriminators, especially in high-resolution or fine-grained image tasks. Another major pillar is gradient penalties, epitomized by the WGAN-GP framework. Instead of enforcing a strict weight constraint, we penalize deviations of the discriminator's gradient norm from one-on samples interpolated between real and fake data. This directly promotes a one-Lipschitz critic, yielding smoother updates and often better coverage of the data modes. The result is typically improved stability, faster convergence, and fewer pathologies like sharp artifacts or repeated modes. Evaluation matters just as much as architecture. Freshet inception distance, or FID, has become a workhorse metric. It compares real and generated distributions in a learned feature space, capturing both quality and diversity. But FID is not perfect. It depends on the feature extractor and can be misleading on certain datasets. Hence, many researchers report complementary metrics such as inception score and, increasingly, precision recall analysis for generative models to separate sample quality from coverage. Phasing in additional diagnostics, latent space interpolation tests, human studies, or task-aligned metrics provides a more robust assessment of a model's capabilities. Hybrid models and architectural innovations also broaden what GANs can do. Conditional GANs tailor generation to labels or attributes, enabling controlled synthesis. Style-based generators, as in StyleGAN, deliver high-fidelity, disentangled representations that allow fine-grained stylistic control. Progressive growing of GANs facilitates training stability for high-resolution images. Beyond pure GANs, VAE-GAN hybrids, and information theoretic variants like InfoGAN, combine reconstruction signals or latent disentanglement objectives with adversarial training. More recently, diffusion models and GAN hybrids push the frontier on sample quality and diversity, prompting ongoing cross-pollination. Ethically, we must remain vigilant. With greater realism comes greater responsibility. Yet with robust evaluation, stabilization techniques, and thoughtful model design, GANs continue to be a powerful, extensible framework for researchers seeking to study and harness generative learning. The core message endures. Two networks in a well-regulated loop drive progressively more convincing and useful data. Beyond their ability to generate convincing images, modern GANs are being steered toward reliability, controllability, and rigorous evaluation. In research settings, we ask, not only can it synthesize realism, but how can we quantify quality and diversity, ensure stability, and deploy responsibly? To that end, several advanced mechanisms have become mainstream. First, stability and control. Spectral normalization regularizes the discriminator by constraining its weight magnitudes, which helps prevent the kind of explosive feedback that derails training. Gradient penalties, most notably the WGAN-GP approach, impose a Lipschitz constraint via an explicit penalty on gradients, promoting steadier learning dynamics and reducing mode collapse. Alongside these, practical tricks such as balanced updates, learning rate schedules, and careful architectural choices keep the generator and discriminator in a productive dialogue rather than spiraling into instability. These techniques do not just improve convergence, they enable experiments that probe model capacity, conditioning, and latent space structure with greater reliability. Second, evaluation metrics that go beyond intuition. The Fréchet inception distance has become a standard because it compares the statistics of real and generated images in a feature space that correlates with perceptual quality. It is complemented by the inception score and by newer, distribution-focused measures like precision and recall for generative models, which separately quantify realism, precision, and diversity recall. Researchers also use perceptual or task-driven losses to assess alignment with human judgments and controlled ablations to understand how conditioning and latent traversals affect outputs. A rigorous evaluation pipeline often combines these metrics with qualitative assessments to capture both fidelity and variety. Third, hybrid and evolving architectures. Hybrid models, GANs, that pair with VAEs, normalizing flows, or diffusion-based components seek the strengths of multiple paradigms. The sample quality of adversarial training with better latent representations or robust sampling dynamics from diffusion schemes. Style-based architectures, such as style GAN families, offer precise disentanglement of global and local features, enabling fine-grained control over appearance. Hybrid approaches can also help in domains with limited data, where combining generative priors with supervised objectives improves sample efficiency. Finally, applications and responsibility. GANs unlock data augmentation, synthetic datasets for rare conditions, and rapid prototyping across entertainment, healthcare, and fashion. They also demand careful consideration of ethics, labeling, and bias. We should embed safety checks, transparent disclosure of synthetic origin, and ongoing audits of data sources and model behavior. In short, the field is advancing towards stable training, robust evaluation, and responsible deployment, while expanding the creative and practical horizons of what GANs can achieve. Today, we zoom into the generator, turning noise into believable data and learning to fool the discriminator by mirroring real patterns. The generator starts from random input and, through countless updates, aligns its output with the real data distribution. Think of a painter who begins with random blobs and gradually imitates a reference portfolio. We'll then unpack the input noise vector, a fixed length, random array that seeds each run and injects variation so every pass yields something new. Next come network designs and variants, convolutional backbones, residuals, U-shaped architectures, and special flavors like DC GAN, conditional GAN, and style GAN that shape clarity, stability, and control. Why design choices matter? They boost realism and speed learning. In the big picture, the generator works in tandem with the discriminator, the self-improving tug-of-war that yields convincing images, sounds, or text. Up next, how the discriminator judges and guides progress. Let me extend the role of the generator beyond the basics and connect it to the cutting-edge practices researchers are putting to work today. The generator's core task remains: map random noise to data samples that live in the same distribution as real data, guided by feedback from the discriminator. But the way we achieve that mapping has profound implications for stability, controllability, and realism. Modern work treats the generator not as a single monolithic block, but as a design space we tune with regularization, architectural choices, and auxiliary objectives that shape the learned distribution. A central lever is how we constrain and regularize the generator's learning dynamics. Spectral normalization, originally proposed for stabilizing discriminators, is now often applied to generator modules as well to cap the Lipschitz constant of learned mappings. This helps prevent explosive gradients and keeps training stable as the discriminator becomes more powerful. Gradient penalties, most famously the WGAN-GP approach, add a softly enforced constraint on gradient magnitudes to promote smoother, more interpretable updates. Together, these techniques reduce mode collapse and encourage the generator to explore diverse regions of the data space rather than collapsing to a narrow set of modes. The input noise vector remains the seed of variety, but the community has pushed beyond a fixed simple Z. Style-based architectures, such as style GAN, introduce a mapping network that transforms Z into an intermediate latent code W and then modulates the generator's layers with styles derived from W. This decouples global structure from texture and enables nuanced control over features like color, pose, and texture. Tricks like truncation improve sample fidelity at the cost of diversity. Attention mechanisms, self-attention layers within the generator enable long-range coherence, essential for high-resolution, structured data such as faces or scenes. We also see a spectrum of network designs and hybrid objectives. DCGAN-like deep convolutional stacks emphasize stable, progressively refined features, conditional variants inject labels to guide generation, and more expressive forms like StyleGAN2 thirds incorporate architectural refinements, weight demodulation, path length regularization to reduce artifacts while preserving control. Hybrid models fuse GANs with other paradigms. VAE GAN blends reconstruction and adversarial losses for better latent space structure. InfoGAN explicitly maximizes mutual information to make latent factors interpretable. And large-scale, class-conditional GANs, big GANs, demonstrate how scaling and conditioning enhance realism and diversity. Evaluation now routinely includes FID and related metrics, freshet distance on learned features, sometimes complemented by kernel-based measures, K, and precision recall analysis to capture both quality and coverage. Yet, we remain mindful of their limitations and often pair quantitative scores with qualitative audits or human judgments. Beyond the basic role of a binary judge, the discriminator in modern GAN practice is a carefully engineered critic that shapes both stability and realism in generation. Its feedback is not just a label, real divided by fake. It provides gradient information that guides the generator through the high-dimensional landscape of possible outputs. In practice, we monitor how the discriminator signal evolves across training iterations, and we design it to deliver informative, not vanishing gradients to the generator. To stabilize training and improve sample quality, several architectural and regularization techniques are common. Spectral normalization constrains the spectral norm of each weight matrix in the discriminator, effectively bounding its Lipschitz constant. This keeps the discriminator from becoming unrealistically overpowering and helps the generator receive meaningful, well-behaved gradients. In parallel, gradient penalties, most notably the WGAN-GP penalty, enforce a smooth Lipschitz continuous critic by adding a penalty term on the norm of the discriminator's gradient with respect to its inputs. These penalties mitigate issues like gradient explosion or saturation and tend to produce more stable convergence paths, especially in high-dimensional data regimes. The framing of the discriminator's objective has also evolved. In the original GAN setup, it outputs a probability that an input is real. In Wasserstein-based formulations, the discriminator, often called a critic, outputs a scalar score, and training relies on distance-like objectives rather than strict cross-entropy. Regardless of formulation, the core idea remains. The discriminator's feedback shapes the generator's updates through backpropagated gradients, steering outputs toward regions that resemble real data without collapsing to a narrow mode. We also need robust ways to quantify progress. Freikuth inception distance (DFID) has become a standard metric. It compares the distributions of real and generated samples in a learned feature space, capturing both fidelity and diversity. Lower FID indicates samples that are both realistic and varied. In practice, researchers supplement FID with other signals such as inception score, precision divided by recall for data manifolds, and qualitative human judgments to obtain a holistic view of generation quality. Discriminator design also interacts with hybrid models. Techniques like VAE GANs fuse probabilistic latent models with adversarial feedback. InfoGAN introduces mutual information objectives to structure latent spaces. StyleGAN and related architectures employ progressive growing, style modulation, and conditioning to stabilize training and enhance controllability. The discriminator thus remains central, but it increasingly functions within a broader toolkit that includes normalization strategies, penalty terms, and hybrid objectives to push GANs toward both realism and utility. Tonight, we peek behind the curtain of GANs, where a generator and a discriminator stage a careful tug of war. The goal isn't to win outright, but to keep both players improving in step. In the next slides, we'll drill into how different learning signals shape that dance, stable gains with sustained distance, gentler feedback with least squares, and safeguards like gradient penalties and feature matching that keep updates constructive. We'll see how these losses, cut down mode, collapse, and vanishing gradients, and why choosing when and how fast to learn matters. Then we switch to the knobs you actually tune: separate learning rates, adaptive optimizers, batch sizes, and epoch counts. We'll discuss how to run small tests, read results, and pick settings that keep training steady while pushing for more diverse, realistic outputs. The minimax view of GAN training is a formal way to describe the push and pull between two neural networks. But to move from a conceptual tug of war to reliable practice, we enrich this picture with stability mechanisms and robust evaluation. In modern setups, the discriminator is not just a blunt critic. It acts under constraints that prevent it from becoming either unbearably strong or utterly brittle. One principal constraint is spectral normalization. We constrain the spectral norm of each weight matrix in the discriminator. This throttles the Lipschitz constant of the network, producing smoother, more interpretable gradients for the generator and reducing sharp, destabilizing updates. Beyond spectral normalization, gradient penalties provide a direct way to enforce smoothness of the critique. The WGAN-GP approach adds a penalty on the gradient norm of the discriminator with respect to samples interpolated between real and fake data. This keeps the discriminator from learning abrupt boundaries and helps the generator receive meaningful gradient signals even when the two players are on the edge of collapse. Variants like Dragon or other gradient penalty schemes extend this idea to ensure stable learning across different data regimes. On the objective side, many practitioners move beyond the vanilla minimax loss. Hinge loss, for example, often yields sharper decision boundaries and more stable updates. A common practical rule is to adopt a 2-time scale update rule. Give the generator and discriminator different learning rates so that neither outpaces the other too aggressively. This aligns with the intuition that simultaneous optimization requires balanced progress, not an overpowering gust in one direction. Evaluation becomes essential in diagnosing progress. The Frechet inception distance (FID) has become a standard metric. It measures how close the generated distribution is to the real distribution in a learned feature space, capturing both fidelity and diversity. Complementary measures such as inception score, precision divided by recall for distributional coverage, or perceptual similarity metrics (EG) offer additional lenses on quality and variety. Regular quantitative evaluation helps detect mode collapse early and guides architectural or training adjustments. Hybrid approaches extend the adversarial paradigm by integrating ideas from other generative families. VAE GAN hybrids fuse reconstruction-centric objectives with adversarial refinement. Diffusion-inspired refiners can act on GAN outputs to remove remaining artifacts. Conditional extensions, auxiliary classifiers, and feature M-matching losses further enrich the learning signal, often improving diversity without sacrificing realism. In practice, you will monitor gradient norms, track FID over epochs, and watch diversity metrics alongside loss curves. If the generator improves but diversity stalls or the FID plateaus, recalibrate learning rates, reintroduce gradient penalties, or consider a unrolled GAN style stabilization. The key takeaway is that the minimax game is tamed not by brute force but by a thoughtful mix of constraints, diagnostics, and hybrid strategies that keep both players learning toward better, more varied data. Here, we extend the picture beyond the basic tug of war to the concrete mechanisms that keep learning stable and meaningful. The core idea remains the same. The generator and discriminator push and pull, but the way we shape their signals and evaluate progress matters a great deal for researchers who need reliable convergence and diverse, high-quality outputs. First, consider how we constrain the discriminator. A common and effective approach is spectral normalization. By normalizing the spectral norm, the largest singular value of each weight matrix, we impose a soft Lipschitz constraint on the discriminator. This prevents it from becoming excessively confident and producing extreme gradients, which can destabilize the generator. In practice, spectral normalization helps the training dynamics be more predictable across different architectures and datasets, making it easier to compare experiments. Second, gradient penalties offer a direct way to enforce stability. The WGAN GP framework introduces a gradient penalty on samples sampled along straight lines between real and fake data. The penalty encourages the discriminator's gradient norm to stay near 1, which preserves meaningful gradient flow for the generator even after many training steps. This approach typically yields smoother optimization landscapes than simple cross-entropy based losses and reduces oscillations that lead to mode dropping or collapse. Third, alternative loss formulations beyond the original minimax objective have shown practical benefits. Least squares GAN, LS-GAN, replaces the binary cross-entropy with a squared error, which tends to keep gradients alive when the discriminator is confident, mitigating vanishing gradient issues. The hinge loss, popular in many GAN variants, provides a robust margin that often stabilizes training and yields sharper samples. These losses illustrate a broader principle, shaping the error surface to maintain informative gradients as training progresses. Fourth, several stabilization and improvement techniques fall under the umbrella of hybrid models. Feature matching steers the generator to replicate intermediate statistics, textures, and structures learned by the discriminator, not just fooling the final decision boundary. Unrolled GANs explicitly backpropagate through several discriminator steps, dampening oscillations. More recent architectures introduce self-attention and hierarchical conditioning, and crucially hybrid models that combine GAN objectives with variational autoencoder, components, VA GAN, or encoder-based conditioning to improve latent representations and reconstruction fidelity. Fifth, evaluation matters. Metrics like fresh at inception distance, V, quantify both realism and diversity by comparing feature distributions of real and generated samples. Kernel inception distance, KID, and precision recall plots offer complementary views of quality versus coverage. Relying on a single metric can be misleading. A robust study reports several metrics to assess both sample quality and mode coverage. In this part of the talk, we move from the basics of tuning to a more rigorous, evidence-informed approach to hyperparameters that directly shape stability, convergence, and sample quality in GANs. The goal is not to chase a single best setting, but to build a robust regimen that reveals how small changes ripple through training, dynamics, and evaluation metrics. First, we refine learning rate strategies and optimizers with an eye toward two-player dynamics. Keep separate learning rates for the generator and the discriminator, but move beyond fixed values. In practice, you'll often adopt a 2-time scale update rule, a relatively slower discriminator and a somewhat faster generator, or vice versa, depending on where instability tends to originate in your architecture. Adaptive optimizers, ADAM, ADAM-W, or RMSprop, help because they adjust step sizes by gradient statistics, which is crucial when the two networks push and pull the loss landscape in tandem. If you notice the discriminator overpowering the generator, nudge its learning rate down a notch or give the generator a modest LR increase, and vice versa. Do not rely on a single magic value, monitor gradient magnitudes and loss oscillations as you vary these rates. Next, incorporate stabilization techniques that address the core issue, the Lipschitz behavior of the discriminator, and the gradient flow to the generator. Gradient penalties, as in WGAN, GP, or DRAGON, and spectral normalization on the discriminator are now standard tools. A gradient penalty enforces a soft Lipschitz constraint, reducing gradient explosion and mode collapse, while spectral normalization directly constrains the discriminator's weight spectral norm, often yielding smoother, more stable updates and enabling larger batch sizes without sacrificing generalization. When using gradient penalties, you'll frequently adjust the penalty coefficient lambda to balance the penalty term against the standard adversarial loss. Then, consider batch size, epochs, and precision. Batch size interacts strongly with learning rate and stability. Small batches inject noise that can help escape poor local dynamics, while large batches can accelerate samples but may reduce diversity. Gradient accumulation can emulate large batches without excessive memory use. Mixed precision training speeds things up but demands careful loss scaling to maintain stable updates. Monitor for overfitting signs not just with the discriminator's accuracy, but with evaluation-driven indicators, see below, to determine an appropriate epoch ceiling. Evaluation and stopping deserve deliberate attention. Use robust metrics such as freshet inception distance (FID) to assess distributional similarity between real and generated images, augmenting with LPAPS for perceptual similarity and precision divided by recall for distribution coverage. Avoid relying solely on inception score. Use a fixed evaluation set to compute these metrics across runs to detect genuine improvements versus overfitting or memorization. Hyperparameter searches should be guided by improvements in these metrics, not by localized gains in training loss alone. Finally, when you work with hybrids, GAN, VE, GAN flows, or multi-scale discriminators, expect different sensitivities. Learning rates, penalty weights, and normalization choices may shift. Design your experiments with controlled ablations and use principled search strategies, Bayesian optimization, hyperband, or population-based training to map the landscape efficiently. Keep thorough logs, seeds, configurations, metrics, and runtimes. The art of hyperparameters here is iterative, evidence-driven refinement that stabilizes training while delivering genuinely novel samples. First, we rely on loss trajectories as our primary diagnostic. The loss curve is not a single number but a narrative of optimization. How the model's error evolves as it processes more data, updates its parameters, and refines its representations. We watch for smooth, monotonic improvement or for troubling plateaus and sudden spikes that signal instability. Loss alone doesn't tell the whole story, but when it is considered alongside outputs, it becomes a powerful early warning system. Second, generated sample grids offer a fast, tangible readout of output quality across the model's input space. Rather than waiting for a full evaluation, you glance at a grid of samples to see whether the model is producing diverse, plausible results or whether it's collapsing to a narrow set of outputs. This visual quick check is invaluable for catching mode collapse and other pathologies in near real time. Third, we deploy dimensionality reduction tools like TSNE to map high-dimensional data into 2 dimensions. This isn't about a flashy plot. It's about seeing structure in the latent representations and how they evolve during training. A stable progression often correlates with coherent clusters and smooth transitions across epochs. When the map looks chaotic or overlaps collapse, it's a signal to pause and reassess. Along with these, feature maps give a window into the model's internal signals. By inspecting activation patterns across layers, you can verify that information flows as expected and that salient features are being amplified rather than drowned out. Regular visualization and inspection are not cosmetic. They are part of a robust safety net. They help you identify 3 classic problems: mode collapse, vanishing gradients, and unstable training. If you spot any of these, adjust the learning rate schedule incrementally, consider smaller steps, add data, or experiment with alternative architectural choices. The goal is to restore a healthy learning dynamic, not to chase an elusive perfect plot. Checkpointing is the practical backbone of this workflow. Treat it as bookmarks. In a long book, save states at sensible intervals so you can rewind to a known good moment. A simple rule of thumb is to save every few thousand training steps and retain the most recent dozen checkpoints. Each save should capture essential state information, weights, optimizer status, and any scheduler state, so rollback and comparison are meaningful. The RTX 30, 40, and 50 series give you headroom to train larger generators and discriminators, but the real gains come from pairing that compute with stability techniques, robust evaluation, and scalable pipelines. First, stability mechanisms. In current practice, spectral normalization is a reliable way to constrain the discriminator's Lipschitz constant, reducing volatility in the gradient updates. Pair that with a gradient penalty as in WGANGP to enforce smoothness on interpolated samples, typically with a weight around 10, and you'll see more stable convergence and fewer mode collapses. Consider also path length regularization for the generator to encourage consistent, smooth changes in outputs as latent codes vary. These tools aren't just for show, they directly affect the quality and diversity of the samples, especially when you scale up model capacity. Second, Robust evaluation is essential beyond subjective quality checks. The Frechet inception distance (FID) remains a go-to metric for comparing distributions of real and generated images in feature space. Use a fixed, domain-appropriate feature extractor, often inception v3 or a suitable backbone, and report FID on a held-out validation set, averaged over several seeds or a moving window to capture stability over time. Track kernel inception distance key as a complementary metric less sensitive to sample size. Include perceptual similarity metrics like LPAPS to quantify human perceived differences, and where relevant precision recall analysis to assess both fidelity and diversity. Remember that metrics depend on data and evaluation protocol. Document your pipelines and run multiple trials for confidence. Third, be open to hybrid architectures. GANs can be augmented with diffusion ideas or contrastive losses to improve training signal and sample quality. For example, auxiliary tasks such as instance discrimination or contrastive regularization can stabilize learning when you push model capacity higher. Hybrid training objectives combining adversarial losses with denoising or reconstruction objectives often yield better generalization on complex datasets. Fourth, practical training optimizations. Mixed precision FP16 or bfloat16 with automatic scaling accelerates training and reduces memory, especially on multi-GPU runs. Use gradscaler and consider gradient accumulation to simulate larger effective batch sizes without exceeding memory. In multi-GPU settings, favor data parallelism, distributed data parallel in PyTorch, and minimize inter-GPU communication bottlenecks. Align data pipelines with prefetching and pinned memory, and monitor memory usage to prevent slowdowns or crashes. Memory-hungry steps benefit from gradient checkpointing and careful scheduling of compute-heavy operations. Next, we zoom into how different GAN ideas shape what we can generate. We'll start with conditional GANs, where labels steer both the generator and the discriminator, letting us guide outputs from a red fish in a bright scene to multiple variations from a single description. We'll see concrete use cases, image-to-image translation, text-to-image synthesis, and domain adaptation, plus how labels influence color, style, and mood. Then we turn to DC GANs, which use convolutional layers to capture spatial structure with design choices that improve stability, strided convolutions, removing fully connected layers, batch normalization, and ReLU versus leaky ReLU rules. After that, we explore families that tackle training hurdles. WGANs Earth Mover distance for steadier learning, CycleGANs unpaired image translation with cycle consistency, and StyleGAN variants that give fine-grained style control. Expect connections to practice and design intuition for your projects. Conditional GANs extend the conditioning idea well beyond simply pairing a label with input data. Today, I'll expand on how we can strengthen, evaluate, and extend these models in practice, focusing on stability, conditioning mechanisms, and robust evaluation. First, stabilization and regularization. In conditional settings, the discriminator's job is harder because it must assess not only realism but also label consistency. Techniques such as spectral normalization apply to the discriminator and sometimes the generator, constrain the Lipschitz constant, and help control weight magnitudes during training. Coupled with gradient penalties, as in WGAN-GP, we encourage the model to satisfy a soft 1 Lipschitz condition, reducing mode collapse and oscillations when labels introduce sharp decision boundaries. These tools are especially valuable as you scale to many labels or fine-grained attributes. Second, conditioning mechanisms. A straightforward approach uses label information to modulate features. We can implement conditional batch normalization, where the scale and shift parameters are functions of the label, enabling a smooth and expressive influence of the label across layers. A more discriminative strategy is the projection discriminator, which computes an inner product between label embeddings and features before the final logits, effectively tying the realism judgment to the same semantic space as the labels. There's also the auxiliary classifier (GAN) approach, where the discriminator carries an auxiliary head predicting the label, providing an explicit signal to align generated content with the conditioning attribute. While discrete labels are common, continuous attributes can be incorporated via learned embeddings or conditioning vectors, broadening the design space. Third, evaluation and metrics. Beyond qualitative checks, we rely on quantitative metrics to compare conditional outputs. Frechet inception distance (FID) remains a staple for sample quality and diversity, but we can extend it to condition settings by computing per label FID and aggregating. Additional metrics include inception score, LPIPS based perceptual similarity, and label condition accuracy of auxiliary classifiers. Recent work also advocates distributional metrics that capture how well the conditional distribution Px vertical bar y is approximated, along with fairness-aware evaluations to detect label bias or unintended correlations. Fourth, hybrid models and practical deployment. Hybridizing conditional GANs with diffusion models or VAEs can combine the strengths of precise conditioning with improved coverage of modes. For example, a diffusion backbone can be guided by a conditional adversarial head, yielding stable training and sharper samples for each label. In practice, careful dataset curation, balancing label counts, monitoring for biases, and avoiding overfitting to particular attributes remains essential. Beyond the core setup described for DC GANs, there is a family of refinements that researchers routinely leverage to push stability, realism, and evaluability in image synthesis. I'll outline these advanced ideas and how they complement the practical rules you've already seen. First, stability through the discriminator's behavior. Spectral normalization has become a standard tool for constraining the Lipschitz constant of the discriminator, which in turn tames gradient magnitudes flowing back to the generator. In practice, you can apply spectral normalization to each convolutional layer in the discriminator and often in the generator as well. This tends to reduce oscillations, mitigates sharp gradients that derail training, and helps prevent mode collapse that can plague deep connects. If you prefer a broader loss grounding approach, gradient penalties as in WGAN GP or hinge penalty variants explicitly enforce smooth gradients with respect to inputs, providing a principled path to stable learning in adversarial settings. Pairing these penalties with a 2-time-scale update rule, typically, a slower, more cautious update to the generator relative to the discriminator often yields more reliable convergence across datasets. Second, evaluation and diagnostics. The Freshet inception distance FID has become the go-to metric for balancing realism and diversity. It compares distributions of real and generated images in a feature space extracted from a pre-trained network, offering a continuous, perceptually grounded score. In contrast to the inception score, FID accounts for both sample quality and variety, and is less biased by mode collapse when used with a representative dataset. When reporting results, pair FID with qualitative assessments and, where possible, diversity-oriented metrics A, G. Precision divided by recall in feature space to avoid overfitting to a single number. Third, architectural and training refinements for realism. Self-attention mechanisms, as in SAGAN, enable the model to capture long-range dependencies, producing more coherent textures and global structure. Patch-based discriminators, patch GAN, focus on local image patches, encouraging high-frequency fidelity and better texture detail, while still supporting global coherence when integrated into full image discriminators. Hybrid architectures such as VAE GAN blends or models that incorporate perceptual losses can stabilize training and encourage structured latent representations, aiding disentanglement and controllability of generated content. Finally, practical design choices. Modern DC GAN variants may incorporate perceptual or feature modality objectives, use conditional frameworks for class condition generation, or explore progressive growing to stabilize early-stage learning on high-resolution outputs. These approaches extend the foundational DC GAN recipe, while keeping the core emphasis on stable optimization and credible new imagery. Wasserstein GAN or WGAN gives us a different lens on training generative models by using the Earth mover distance as its loss. The key intuition is that the loss reflects how much mass we must move in data space to transform the generated distribution into the real one, which yields gradients that remain meaningful even when the two distributions barely overlap. This makes learning more stable and often more reliable than traditional GAN losses. Practically, this approach mitigates the wobbly training dynamics, reduces mode collapse, and helps gradients stay informative throughout training. A helpful analogy is a factory producing toy types. With WGAN, we don't chase only one color of ball. The distance measure preserves diversity by better guiding the generator toward the full support of the data distribution. Beyond the basic WGAN, several refinements have sharpened stability and sample quality. The original weight clipping strategy to enforce a Lipschitz constraint was simple but harsh, often underutilizing network capacity. A more widely adopted advance is the gradient penalty, which softly enforces the one Lipschitz condition by penalizing deviations of the discriminator's gradient norm from one non-interpolated samples. This yields smoother training dynamics and often better fidelity. Another complementary route is spectral normalization, which constrains the spectral norm of each layer's weight matrix, providing a stable, parameter-efficient way to impose a Lipschitz bound without relying on penalties alone. When combined with thoughtful architectural choices and discriminators, these techniques improve convergence, reduce gradient explosions, and help maintain sample diversity. As researchers, we also rely on robust evaluation fit scores, precision recall for generative models, and perceptual or feature-based metrics to quantify both quality and coverage of the generated distribution. CycleGAN brings a different angle, unpaired image-to-image translation with cycle consistency. Instead of requiring matched pairs, it learns mappings between domains A and B by enforcing that translating A to B and back to A recovers the original content. This preserves structure while allowing style or domain changes, which is invaluable for art, photography, and design tasks. However, cycle consistency alone isn't always sufficient. Additional losses such as identity mappings, perceptual losses, or domain-specific priors can help preserve semantics and reduce unintended alterations. StyleGAN and its successors illustrate the other axis, control. The style-based generator uses a mapping network to separate high-level attributes from stochastic details, enabling cores to find control over appearance, lighting, texture, and other attributes. Innovations across StyleGAN versions have tightened realism, reduced artifacts, and introduced more nuanced style mixing and truncation controls, with continuing work addressing aliasing and training stability in real-world modes. Together, these variants illuminate how changing distance measures, cycle rules, and style control shape results, and how the field keeps evolving year after year. Next, we widen our lens to see how GANs move from still pictures into broader creative and scientific work. The upcoming slides show video frame prediction, where a generator and discriminator forecast future frames, producing smoother motion, lifelike expressions, and consistent characters for films, games, and immersive apps. You'll see how designers use this to speed up animation and keep scenes aligned with human input guiding the craft. Then we turn to data augmentation. GANs generate diverse, realistic samples to balance limited datasets, boosting learning when data is scarce. Text-to-image synthesis follows, translating descriptions into visuals that spark ideas and support human-computer interaction. We also explore medical imaging advances, super-resolved scans, synthetic data for training, and safer analysis. Finally, we'll discuss ethics, privacy, and validation, how to use these powerful tools responsibly and transparently with practical classroom exercises to experiment safely. Let me take you beyond the basic two-player story and into the frontier where GANs become stable, measurable, and genuinely useful in research workflows. First, stabilization is the key enabler of practical GANs. A central idea is to control the discriminator's capacity so it cannot overfit or oscillate wildly. Spectral normalization is a lightweight, effective tool. By constraining the spectral norm of each layer's weights, we bound the Lipschitz constant of the discriminator, which tends to produce smoother gradients for the generator. Complementing this, gradient penalties enforce a soft constraint on the gradient norm. The Wasserstein GAN with gradient penalty is a canonical example. The penalty on interpolated samples between real and fake data encourages the critic to behave in a one Lipschitz manner, reducing training instability and improving convergence. There are related regularizations, such as R1 divided by R2 penalties on real or fake data, and practical tips like using TTUR, different learning rates for the generator and discriminator to further stabilize training. In tandem, architectural choices such as progressively growing networks or style-based generators help the model learn core structure first and refine details later, producing sharper, more coherent outputs. Second, robust evaluation is essential for scientific credibility. The Frechet inception distance has become a standard because it estimates how close the distribution of generated images is to the real distribution in a learned feature space. However, FID has caveats. It can be sensitive to dataset size, pre-processing, and domain shifts. Complementary metrics matter. The kernel inception distance, key, provides an unbiased alternative based on maximum mean discrepancy. Perceptual metrics like precision and recall for generative models help quantify fidelity versus coverage, highlighting mode collapse or lack of diversity. Some researchers also use perceptual path length and human studies for nuanced judgments. The practical rule is to report multiple metrics, specify evaluation protocols, sample size, seed repeats, and pre-processing, and be transparent about limitations. Third, hybrid approaches offer practical benefits by marrying GANs with other paradigms. Hybrid models can blend the sharpness of GANs with the stability or interpretability of diffusion or VAE-based methods. For example, GANs can provide a strong prior or fast refinement in diffusion-based pipelines or be integrated into style and content-aware architectures as seen in style-based generators and conditional variants. In super-resolution and image-to-image tasks, these hybrids often yield better detail preservation and fewer artifacts than pure GANs alone. As you design and evaluate your experiments, keep ethics and bias in view. Use rigorous evaluation, document data provenance, and interpret results in the context of the domain. With stabilized training, robust metrics, and thoughtful hybrids, GANs become powerful, trustworthy tools for advancing research and creative inquiry. Today, we move beyond the core GAN framework to the techniques that make video frame prediction reliable, scalable, and evaluable in real-world research settings. The promise is clear: predict temporally coherent frames that respect motion patterns while keeping training stable and results interpretable. A central advance is architectural and regularization design for temporal models. Instead of treating frames as independent outputs, modern approaches couple spatial realism with temporal consistency. We often use 3D convolutions or con-LSTM blocks to capture short and long-range motion, and increasingly, transformer-inspired temporal encoders to model dependencies across multiple frames. Hybrid cues, such as incorporating estimated optical flow as an auxiliary target or constraint, guide the generator toward plausible motion trajectories without forcing exact pixel matches. This yields smoother transitions, more natural motion, and fewer jarring flickers. Stability and generalization are addressed through careful regularization and loss design. Spectral normalization stabilizes the discriminator by constraining its Lipschitz constant, helping prevent over-enthusiastic gradients that derail learning. Gradient penalties, as in WGA and GP, enforce smoothness of the critic's response and often improve convergence in video settings where temporal feedback loops can amplify errors. These tools pair with well-chosen loss terms: perceptual losses based on pre-trained networks, feature matching losses, and explicit temporal coherence losses that penalize frame-to-frame inconsistencies. The result is not just realistic individual frames, but consistent motion and lighting across sequences. Evaluation has caught up with these capabilities. Beyond frame quality measures like FID and LPAPS, practitioners now rely on freshet video distance, FED, to quantify temporal realism, as well as temporal consistency metrics, and when possible, human studies to assess perceived smoothness. Ablation studies on temporal receptive fields, perceptual versus adversarial losses, and regularization strengths are essential to understand what drives improvement in a given domain. Hybrid modeling is another fruitful direction. Some systems couple GANs with optical flow pipelines or physics-inspired constraints to ensure physically plausible motion and object interactions. Others explore integrating diffusion-like diffusion steps for better diversity while maintaining temporal coherence. All of these strategies aim to balance fidelity, coherence, and diversity of predicted sequences. Finally, consider ethics, data quality, and practical deployment. Robust datasets, transparent reporting of synthetic content, and clear guidelines for when and how frame prediction is used are critical as these tools move toward production in films, games, and virtual environments. With disciplined design and rigorous evaluation, frame predicting GANs can reshape how artists plan, prototype, and iterate across time. As we push these applications forward, a set of advanced techniques and evaluation practices increasingly shapes what we can reliably deploy. I'll sketch several threads that go beyond the basics and are now central in research and practice. First, data augmentation. Beyond simply more samples, we can harness stabilization and diversity with techniques like spectral normalization in the discriminator and gradient penalties, as in WGA and GP, to keep training stable when the augmented data are highly variable. We also see progress with augmentation policies that adapt during training, balanced, domain-aware augmentations that preserve label semantics while expanding variation. In practice, this means generating not just more images, but more useful variants. Different lighting, poses, or sensor characteristics evaluated with metrics that capture both realism and coverage. For small or imbalanced datasets, these sophisticated augmentations can substantially improve downstream model performance, particularly when the augmented pool better spans the real-world manifold. Second, text-to-image synthesis. Conditioning now leverages powerful cross-modal encoders and attention mechanisms. Cross-attention between text and image features enables finer control over color, texture, and composition, while clip-guided guidance helps align generated visuals with semantic intent. Evaluation increasingly uses perceptual metrics such as clip scores alongside traditional image fidelity measures. From a design perspective, prompt engineering and interactive controls let researchers iterate rapidly, testing how subtle phrasing shifts affect output. This accelerates ideation for designers and researchers while highlighting the need for robust alignment between the language prompt and visual result. Third, medical imaging. GANs contribute not only to super resolution and reconstruction for MRI and CT, but also to synthetic data generation for training diagnostic models under privacy constraints. High resolution generation, denoising, and realistic phantoms can mitigate data scarcity and scanner heterogeneity. However, clinical deployment demands rigorous validation, PSNR and SSIM for image quality, plus radiologist-led assessments and task-based metrics A. G. Diagnostic accuracy, lesion detectability. Privacy-preserving strategies, differential privacy, federated learning, or privacy-aware synthetic data are essential to minimize leakage and comply with audits and consent. Domain shift, different scanners, protocols remains a critical concern, so cross-site validation is a must. Fourth, evaluation and hybrid modeling. Beyond freshet inception distance, practitioners now use kernel inception distance, KID, improved precision divided by recall measures for generative models and task-centric evaluations. Hybrid models, GANs, paired with VAEs, flow-based models, or diffusion approaches offer better diversity and fidelity, trading off training time or computational cost. In some settings, diffusion or score-based components guide GANs to higher fidelity, while keeping the sample generation speed practical for iterative design workflows. In short, these advances push GANs toward more reliable augmentation, more controllable synthesis, and clinically responsible image generation, all while demanding careful validation, governance, and ethical stewardship. Before we dive deeper, let's connect what we've just outlined to what comes next. We'll unpack a common pitfall in generative models when the system narrows to a limited set of outputs, why it happens, and how we push for richer variety. We'll walk through 3 practical remedies: teaching the discriminator to compare samples in a batch, the generator forecasting near-future feedback, and guiding outputs with statistics from real data. Then we rise to how GANs can pair with reinforcement learning, a 2-player dynamic where the generator and the critic push one another, and agents learn from trial and error in changing environments. We'll also glimpse multi-agent scenes and how such setups support safer, richer simulations. Finally, we'll address responsibility, detecting deepfakes, sourcing data openly, and implementing clear rules to keep innovation aligned with society's interests. Mode collapse remains a central challenge. The generator settles on a narrow set of outputs, the diversity of samples erodes, and training becomes brittle. The core diagnostic remains an imbalance in the game between generator and discriminator. The generator learns to exploit a few weaknesses. The discriminator overfits those tricks, and the result is a shrinking manifold of plausible outputs. For researchers, the task is not only to push for realism, but to guarantee breadth of coverage across the data distribution. While the slide highlights 3 concrete strategies: mini-batch discrimination, unrolled GANs, and feature matching, there is a broader stabilization and evaluation toolkit that complements these ideas and guides principled practice. Beyond the 3 strategies, 2 stabilization levers are now standard in modern GAN work. First, spectral normalization constrains the Lipschitz constant of the discriminator by dividing its weight matrices by their spectral norm. This prevents the discriminator from becoming unrealistically sharp and ensures the generator receives well-behaved gradient signals across training iterations. Second, gradient penalties, as in WGAN-GP, impose a soft constraint on the gradient norms of the discriminator with respect to its inputs. This smooths the loss landscape, curbs oscillations, and reduces the tendency of the generator to chase transient discriminator weaknesses. In tandem, these tools decouple the relative pacing of G and D and yield more stable convergence paths, which in turn helps preserve diversity in the generated samples. Evaluation metrics are indispensable when addressing mode coverage. Frechet inception distance (FIDI) has emerged as a practical standard. It measures the distance between real and generated distributions in a learned feature space, rewarding not only realism but also diversity. Lower FID indicates that generated samples sit closer to the manifold of real data and cover modes more broadly. Kernel inception distance (AID) and precision recall analysis for distributions offer complementary views of quality versus coverage. Using these metrics during development helps diagnose whether improvements pertain to realism, variety, or both. Hybrid modeling approaches also offer avenues to mitigate mode collapse. For instance, VAE GAN hybrids blend reconstruction incentives with adversarial objectives, encouraging the model to cover data modes that purely adversarial training might miss. Encoder-generator frameworks like ALI, divided by BiGAN, promote bidirectional mappings, which can stabilize learning and improve generalization. When integrated with the three core strategies, such hybrids can yield richer, more controllable diversity without sacrificing sharpness. Today, we deepen the discussion of how GANs and reinforcement learning can work in concert to tackle more sophisticated problems. We already know GANs consist of a generator and a critic, with a dynamic where the generator tries to fool the critic while the critic tries to distinguish real from synthetic data. When we bring reinforcement learning into the picture, we add a learnable, reward-driven component that can guide how these models explore and improve. In practice, the integration often hinges on two ideas. First, the generator can be viewed as a policy that produces data samples, and the critic provides a signal that can be shaped into rewards or cost terms. This opens up policy gradient style updates for the generator, where the reward corresponds to realism, task relevance, or adherence to a desired distribution. Second, reinforcement learning equips the system to adapt to changing environments. By framing data generation as a sequential decision process, the generator learns to craft samples that not only look authentic but also capture the dynamics or variations needed for robust downstream tasks. A key concern in this space is stability and quality, for which several advanced techniques have become standard. Spectral normalization constrains the Lipschitz constant of the discriminator, stabilizing training and reducing oscillations in the adversarial game. Gradient penalties, as embodied in WGAN, GP, or related methods, enforce smoother gradient behavior and help prevent mode collapse. When combined with RL signals, these regularizers help ensure that reward-driven updates do not drive the generator into pathological regions of the data space. Evaluation becomes richer beyond visual fidelity. Frechet inception distance and the related kernel inception distance provide quantitative measures of how close the generated distribution is to the real one, taking into account both mean and covariance in feature space. Precision and recall for generative models offer a lens on mode coverage and redundancy, helping us diagnose whether the model is truly diverse or merely producing a narrow set of samples. When we blend GANs with RL, these metrics guide not just perceptual quality but task-relevant performance, such as how well a policy trained on synthetic data transfers to the real world. Hybrid models are common in practice. GANs can be embedded within broader frameworks that include diffusion-style refinements, variational components, or differentiable simulators, yielding richer, controllable data generation. In reinforcement learning contexts, GAN-generated environments or transition data support domain randomization and model-based planning, improving sample efficiency and robustness. Cross-disciplinary applications flourish. Synthetic language data to bolster chatbots, synthetic sensory scenes for autonomous systems, or anomaly detection that benefits from precisely calibrated false data distributions. As we push forward, we must balance fidelity, diversity, and computational cost, always aligning the generation dynamics with the learning objectives of the oral agent and the scientific questions at hand. Mitigating misuse of GANs is not a one-off task. It requires a concerted blend of robust detection, trustworthy training practices, and solid governance. Today, I'll expand on three pillars that refine what we already outlined: advanced detection and model design, rigorous evaluation, and transparent provenance plus policy guardrails. This is about enabling responsible innovation without slowing down scholarly progress. First, on detection and model design. Beyond building detectors, we can enhance resilience by applying advances from the training side to defenders. Spectral normalization, for example, constrains the Lipschitz constant of networks, which helps detectors generalize across domains and resist some adversarial evasion strategies. Gradient penalties, think WGN-GP or other regularizers that enforce smoothness, can stabilize discriminators and detectors, reducing brittle behavior under novel manipulations. In practice, an effective defense ensemble blends texture and motion-based detectors, temporal consistency checks for videos, and even cross-modal cues, audio cues accompanying a forged image to raise the bar for deception. Hybrid models are particularly promising. A detector that couples a GAN-style discriminator with a diffusion model-based verifier, or a multitask architecture that jointly flags realism, provenance, and manipulated regions. These designs give us richer signals than a single metric and make evasion harder. Second, evaluation metrics and benchmarking. Realism alone is insufficient. We must quantify generalization, provenance, and robustness. Freshet inception distance (FID) remains informative but should be complemented by kernel inception distance (key), precision recall analysis for fake versus real distributions, and calibrated detection accuracy across unseen datasets. Human-in-the-loop evaluations remain essential, especially for perceptual quality and semantic integrity. We should also track temporal stability, how detector performance holds up as techniques evolve, and report results across domains, news, social media, education. Importantly, evaluation should account for governance signals, whether content carries explicit provenance metadata, whether watermarking or cryptographic receipts exist, and the detectability of embedded factual cues. Third, provenance, data ethics, and policy. Transparent data sourcing and bias auditing must be codified. Disclose sources, collection methods, and the rationale for data inclusion, audit for demographic or topical bias, and apply privacy-preserving training where possible. Proactively embed provenance signals, watermarks, tamper-evident generation logs, or verifiable metadata that help downstream users assess authenticity. Alongside technical tools, establish model cards and data sheets that document performance, limitations, and failure modes. Clear regulations and policies act as guardrails. Notices of AI involvement, auditable logs of training and testing, and accountability frameworks for deployment in schools, media, and research. In closing, combine strong detection with principal training, rigorous multimetric evaluation, and transparent provenance. This trio protects privacy, reduces harm, and strengthens trust while preserving the pace of legitimate innovation. For researchers and teachers, cultivate verification habits. For students, practice critical sourcing. And for engineers, share transparent notes on data and evaluation. Together, we can guide GANs toward beneficial, responsible applications. On the way forward, we'll dive into two practical ecosystems that make GANs approachable and powerful. First, TensorFlow and the TensorFlow GAN library give us modular building blocks, flexible architectures, and GPU-accelerated training, plus ready-made components to train, evaluate, and visualize progress. You'll see how a simple generator and discriminator can grow into richer models and how metrics guide you toward more realistic outputs. We'll also peek at TensorFlow's smooth integration with TFGAN and how this speeds experimentation. Next, we turn to PyTorch and PyTorch Lightning, which streamline the workflow with clean, reusable blocks and scalable training across one or many GPUs. We'll cover simplified training loops, scheduling, and getting results faster, supported by a thriving community and abundant tutorials. By the end, you'll know how to prototype locally and scale to larger data and cloud environments. TensorFlow and TensorFlow GAN give us more than just a working GAN setup. They open the door to stabilizing and rigorously evaluating generative models at a research level. Building on the basics, we can push training stability, interpretability, and cross-model comparisons with a few well-chosen techniques and metrics. First, consider stabilization techniques that address the core instability in GANs. Spectral normalization constrains the Lipschitz constant of the discriminator by normalizing the spectral norm of its weight matrices. This keeps the discriminator's responses from exploding and helps the generator receive more informative gradients. In practice, you apply spectral normalization to critical layers in the discriminator and sometimes the generator to reduce sensitive dependence on initialization and training dynamics, often yielding steadier convergence with fewer mode collapse episodes. Gradient penalties offer another robust path to convergence. The WGANGP approach adds a gradient penalty on interpolations between real and fake samples, enforcing that the discriminator's gradients have unit norm along those lines. The penalty term is lambda times vertical bar grad dx hat vertical bar 2 1 circumflex 2, where x hat is an interpolation between a real and a generated sample. Typical choices place lambda around 10, but the optimal value depends on data and architecture. TF-GAN can accommodate these penalties within its training loops, enabling you to compare standard adversarial losses against penalty-based objectives in a controlled way. For evaluation, go beyond the traditional loss curves. The freshet inception distance (FID) remains a strong distribution-based metric. It compares real and generated data in feature space, with lower scores indicating closer alignment to the real data distribution. Complement FID with kernel-based metrics like KID and perceptual metrics such as LPIPS to assess both fidelity and perceptual similarity. IS inception score can be informative but is less reliable for diversity. So report multiple metrics and include confidence intervals over multiple seeds. When reporting metrics, ensure consistent pre-processing, model architectures, and evaluation data splits to enable fair comparisons across experiments. Hybrid models and architectural advances provide additional leverage. Combining VAEs with GANs, VAE, GAN, can stabilize training while preserving rich latent representations. Conditional GANs with auxiliary classifiers enable control generation and disentanglement. Style-based discriminators and generators can be paired with spectral normalization and gradient penalties to explore richer stylistic control while maintaining stability. TFTFGAN supports assembling these hybrids, so you can prototype ideas quickly, compare them with standardized baselines, and quantify improvements with robust metrics. Practical workflow tips: start with a simple generator discriminator pair, then enable spectral normalization, add a gradient penalty, and monitor FID and other metrics as you adjust hyperparameters. Use 2 timescale update rules to tune learning rates for G and D, and keep a clear visualization pipeline with checkpoints, sample grids, and real vs fake comparisons. With these tools, TensorFlow and TF-GAN help you perform rigorous, reproducible experimentation that advances both theory and application. Dynamic computation graphs in PyTorch unlock a level of experimentation with GANs that goes beyond the basics. With this flexibility, you can introduce stabilizing techniques, measure their impact, and iterate rapidly without rewriting large portions of code. 2 advanced regularization avenues worth highlighting are spectral normalization and gradient penalties. Spectral normalization constrains the Lipschitz constant of the discriminator by reparameterizing its weight matrices, typically via NN. Utils. Spectral norm. This keeps the discriminator from becoming too powerful too quickly and helps prevent explosive gradients during adversarial training. Gradient penalties, as popularized by WGAN-GP, enforce a soft Lipschitz constraint by penalizing deviations of the gradient norm from 1 on interpolated samples between real and fake data. Implementing the penalty in PyTorch is straightforward, and the dynamic graph means you can experiment with different penalty strengths, alternative interpolation schemes, or even per-layer penalties to study where instability originates in your architecture. Alongside stabilization, robust evaluation becomes essential as models scale. Move beyond qualitative samples and leverage metrics like Frechet inception distance and kernel inception distance, KID, to quantify both quality and diversity. FID tracks the distributional similarity between real and generated features extracted from a pre-trained network, while KID offers a bias-reduced alternative. Complement these with precision recall style diagnostics and coverage metrics to detect mode collapse or underrepresentation of data modes. When comparing architectures or training schedules, pair metrics with qualitative sanity checks and statistical significance tests to draw sound conclusions. Hybrid models and architectural innovations also benefit from dynamic graphs. You can combine GANs with diffusion or energy-based components, or augment GAN objectives with perceptual losses computed in feature spaces, for example, using a frozen classifier backbone. Spectral normalization and gradient penalties remain compatible in such hybrids, giving you a clean path to stabilize training while exploring richer losses. PyTorch's ecosystem, including mixed precision training with AutoCast and GradScaler, and tools like Torch Metrics, facilitates these experiments at scale. For large models, consider TTUR-inspired training schedules, where the generator and discriminator learn with carefully tuned, possibly different learning rates. On the tooling side, PyTorch Lightning abstracts boilerplate, making it easier to implement complex training loops, custom regularizers, and multi-component GANs while preserving PyTorch's flexibility. It also simplifies distributed training across multiple GPUs with minimal code changes. Combine that with DDP and gradient accumulation to push experiments to larger batches and datasets without sacrificing stability or reproducibility. In short, dynamic graphs coupled with stabilizing techniques, robust evaluation, and scalable training practices empower GAN researchers to probe deeper hypotheses, compare ideas rigorously, and accelerate discovery. To conclude, generative adversarial networks illustrate a dynamic competition. A generator proposes, a discriminator judges, and together they push the boundary of synthetic visuals. This deck traced the path from basic GANs to a future of safer, more capable, and more efficient systems. Key challenges remain: training stability, data efficiency, and quality at higher resolutions, controllability via attributes or prompts, robust evaluation, and the thoughtful integration of diffusion-based hybrids, ethics, privacy, and safeguards. The prospect of real-time, on-device tools, and on-demand 3D assets promises new creative workflows in art, science, and education. The overarching message is clear. Progress hinges on imagination, guided by responsibility, transparent methods, open data use, and proactive governance. For students, start with small, ethical projects and learn by building, testing, and sharing. In this part of the talk, we move beyond the core loop and examine emerging architectures and innovations that are reshaping how GANs are trained and evaluated. The aims are sharper stability, richer diversity, and more efficient progress, even as models scale in capability and application scope. A cornerstone of modern stabilization is spectral normalization. By constraining the spectral norm of each layer in the discriminator, we impose a controlled Lipschitz constant, which reduces oscillations and helps the generator receive steadier gradient signals. Closely related are gradient penalties, such as those used in WGAN-GP, which encourage the discriminator's gradients with respect to its inputs to have unit norm. This enforces smoother changes in the decision boundary and mitigates sharp, unstable updates. There are complementary regularizers, like R1 divided by R2 penalties on gradient norms with respect to real or generated data that further damp pathological dynamics. Together, these tools form a more robust training regime that tolerates larger model capacity without succumbing to collapse or divergence. On the evaluation front, more reliable and faster feedback is critical. Frechet inception distance FID remains a workhorse for image quality and distributional similarity, but it is increasingly complemented by metrics such as kernel inception distance, KID, and perceptual-based measures like LP-IPS to capture human judgments of realism. Precision and recall for GANs offer a window into fidelity versus diversity, while class-conditional or multi-scale variants of FID track how well a model preserves detail across resolutions. The field is moving toward standardized cross-domain benchmarks and diagnostic tests that can flag mode dropping and overfitting early in the training cycle. Architecturally, transformer-based approaches are gaining traction. Self-attention enables models to capture long-range dependencies, helping GANs produce coherent textures and structures rather than over-attended micro-details. Hybrid architectures, CNN backbones augmented with lightweight transformers, or patch-level transformers inspired by vision transformers, offer richer context with manageable compute. Advances in adaptive learning rates and scheduler strategies, cosine annealing, one-cycle policies per parameter groups, improve convergence by letting learning rates respond to training dynamics, especially in two-player settings where the generator and discriminator have shifting loss landscapes. Self-supervised objectives are increasingly used as auxiliary tasks to guide representation learning without extra labeling. Tasks such as rotation, prediction, contrastive learning, or pretext tasks encourage the networks to extract structured, transferable features, improving stability and sample efficiency, and often boosting downstream performance in synthetic data generation. Looking ahead, researchers are exploring hybrid models that blend GANs with diffusion refiners, multimodal conditioning, and diffusion GAN hybrids to synergize strengths. The overarching trend is clear: robust training, trustworthy evaluation, and architectures that fuse attention with generation. With these advances, the future of GANs looks brighter, more controllable, and more broadly applicable across science, design, and industry. As we bring this session to a close, I want to thank you for your attentive engagement and the thoughtful questions you raised. Today's exploration of generative adversarial networks has been more than an exchange of techniques. It's been an invitation to consider how these models resonate across disciplines, inform experimental design, and shape the ways we think about data-driven synthesis. What struck me most is how the GAN paradigm acts as a lens for broader research themes. The interplay between learning dynamics and representation, the practical realities of deploying generative systems at scale, and the consequences, both technical and societal, of increasing the fidelity and realism of synthetic data. We've connected ideas from theory to practice, examined how state-of-the-art architectures push the boundaries of what can be generated, and reflected on the trade-offs that accompany greater expressivity with considerations of reliability, evaluation, and robustness. In short, the core questions extend beyond can this be generated to how should we generate, evaluate, and govern what we generate in real-world settings. Ayurveda. Along the way, we've acknowledged the responsibilities that accompany rapid progress in this area. Reproducibility and transparency remain essential. Shared benchmarks, open datasets, and careful reporting of training setups help us compare methods meaningfully. Evaluation, too, has matured from simple similarity metrics to more holistic, multifaceted protocols that capture fidelity, diversity, and downstream utility. And as generative capabilities become more accessible, questions of bias, misuse, and governance demand careful attention from researchers and institutions alike. I also want to leave space for your reflections on how these themes intersect with your own work. Which aspects feel most ripe for rigorous investigation in your domain? Which challenges, whether technical, ethical, or methodological, do you want to tackle next? Your questions today can catalyze new directions, collaborations, or replication studies that strengthen the field. If you'd like to continue the conversation, I'm happy to discuss experimental design choices, dataset considerations, or theoretical implications in more depth. I can share a short reading list and point you toward ongoing projects that align with your interests. Please bring your questions, comments, or critiques, and let's advance this dialogue together.